microphone unmuted. Hello, everybody, and welcome to October. And it's been a fairly busy month, past few months, couple months, and so let's get right to it. And so since the last meeting, we've had a few interesting fun events that occurred. And let's start off with last September 22nd. We have the autumnal equinox. So we're finally halfway between the summer solstice and the winter solstice. And definitely you see the change pretty nicely out there. We've got some nice rain and we see the color. We definitely see autumn. And then Perseverance Mars rover took a fabulous picture, a selfie, they call it. And right now it's in hibernation kind of mode or safe mode. Because Mars is in the solar conjunction. And on September 29th, Ingenuity was trying to attempt its 14th flight, but it couldn't get off the ground. And then there was some problem with the density, air density in that area, and couldn't spin this blade fast enough to get a lift. And so that was a learning experience for them, that they could not get the fast enough RPM to get it off the ground. But they're confident that that will change, and they'll make another attempt when they can for flight number 14. It's doing very, very well, but it was a great learning experience about that density. And as I mentioned, that the Mars missions are facing a 2 weeks communication blackout as the Mars reaches the solar conjunction. And it's going on between October 2nd and October 16th. So I'm sure that they're starting to reconnect with many of those missions even now and continue on. And then just recently, astronomers Hubble was able to see that the red spot is actually spinning a little bit faster, by 8%. And so they've been monitoring the storm, the red spot on Jupiter, and they discovered that it actually is spinning faster lately. And then we have got the moon for October, and the full moon is on October 20th. And you can already look outside. You see a beautiful moon, and it's getting higher as the sun is getting lower. So it's a beautiful sight. And this month of October will be the full hunter's moon. And then we got some beautiful shots in space. This is from the International Space Station of the volcano La Palma. I believe this is the Canary Islands, if I'm correct or not. But look at that shot. It's interesting to see the city light in the vicinity while there's that big, gorgeous lava flow, and it's apparently just flowing pretty fluidly right now. And then just recently, they spotted a new meteor shower, and because of a comet Finlay that passed by, and now they've got a new visible meteor shower that's only visible in the southern hemisphere that peaks around the 7th. So fairly fresh stuff. And then James Webb arrived at Guyana ahead of the December 18th launch. It took him 16 days to ship the James Webb. And so they're still on schedule for the launch on December 18th. And they're concealing the launch time at the moment for security reasons. But I have a hunch, because there's so many thunder and lightning storms that occur at that location, it's probably going to be a very early morning launch, is my guess. And then, I don't know if you heard this, a meteor crash landed in a woman's bed in Golden, British Columbia. How would you like to wake up to that? Okay, heard a loud bang, and she woke up, and there's a meteorite right next to her head. Just missed it. And so this is fairly rare, but they did confirm it. It is actually a meteorite, for one. And so it's a pretty interesting story, to say the least. Boy, she can have that story forever. And so she had no plan to sell it. She wants to hang on to it. It's all hers, but that was quite an awakening for that woman in Golden, British Columbia, so just north of us. And then take a look at this. Beautiful shot. October 12th, we had the Northern Lights. Surprise, surprise. There was some indication there was going to be a strong storm. And that day, I was getting an indication there was going to be about 2%, very slim chance. The weather was decent. I mean, wasn't great, but my understanding, I didn't see it. But the only way you were able to see this was with the DSLR camera, to be able to really pick up on the color. It wasn't exactly a naked eye object. Okay? And so to a layman, it probably would look like a low-lying layer of clouds in the north. But Clifford here got a wonderful shot with the crown point and what have you. But keep in mind, which I'll talk about shortly, that we're moving into cycle 25 and we're seeing a lot of activity. So we're due to have more of these kind of events here in Oregon, not just necessarily next few months, but the next several years as we go into the early stages of the cycle 25. And then on the 13th, Captain Kirk, William Shatner, got up on the Blue Origin and spent nearly 11 minutes up in space. And he's 90 years old, so that makes him the oldest human ever to go up into space. Not bad for being 90. So I know many of us here are qualified now. If William Shatner being 90, all of us can go up there. Right? But if you want to spend a few $100,000 for a 10-minute ride, we'll see. But he was totally mesmerized and profoundly impacted by the view of the Earth on Blue Origin. And then China launched a crew, first China woman astronaut. I forgot what they're called in China, but they were able to send a woman astronaut up on the station, and they're going to spend 6 months in space. And they just launched another vehicle where they're going to have a cargo supply that have food and water and all of that, that will make them hopefully last for 6 months. So China's been very, very busy. And then NASA launched its own robotic mission, Lucy, on a mission to the Trojan asteroids on October 16th. And Lucy will be visiting 8 asteroids over the next 12 years. And then just announced today that Lucy, one of the solar panels didn't quite latch. It's still generating the power, but it didn't go fully latch. And they're going to analyze to see if they can continue with the mission with this. But my understanding, they will be able to. It's very healthy, all of that, but it didn't quite latch. You can see it on the left there. It didn't fully open, but it's still able to generate power and safely go in orbit. And there for cycle 25, the sunspot's been counting quite a bit. It's been going up and up. And I'm expecting that we're going to continue to see this for the next 4 or 5 years. And so we've had quite a few activities, even this video here in the last 48 hours. Look at all the corona mass suggestion, the prominences. You see even some what's called quakes on the surface of the sun. It's been very, very active. And I'm expecting we're going to see more and more of these in the coming months, in the coming years. They're going to see more and more activities on the sun. And you can see just on October 12th, on the far left here, okay, that was where we had the opportunity for the Northern Lights. And that blue bar right there is probably what was visible in Oregon. So for us, in order to see the Northern Lights, the KP needs to be around 6, 7, 8, 9 to be able to reach our latitude. And if it's just around 6, this is just kind of on the border. 5, the slim chance, but I'm confident that we're going to see a northern lights here before long. And so the current forecast, you see it's pretty low, staying around 4. So if you have a trip to Norway, to Finland, to Alaska, Canada, I mean, you can really see some wonderful displays of the northern lights. Looking ahead, and we got the planets still, Jupiter and Saturn still very prominent in the evening sky. Venus is starting to get just slightly lower. And so we still got the usual planets, and Mars is just coming out around the solar conjunction. Neptune and Pluto are right alongside of Jupiter and Saturn. And so still some decent viewing. For the month of November, the full moon is going to be on the 19th, known as the full beaver moon. And then the object for the month is Messier 52. And those of you who are experienced in spotting these Messier objects, this is located in Cassiopeia. And it's a beautiful object, about a magnitude of 5. A beautiful cluster, and generally referred to as the New General Catalog 7657. And it's a nice little object. There's about location on the very last left side of the W of Cassiopeia. And this is called an open cluster. And so it's a fun little one to look at. And mind you that the Cassiopeia is in the circumpolar region. You can actually see this object all year long. And so this is now the ideal time because Cassiopeia is high above the northeast horizon. Before midnight, by the time tomorrow morning, it's nearly overhead. So it's a great time to view M57. And for the space station, it'll be visible through November 10th. I do want to mention that there's a nice documentary on Disney Channel right now called Among the Stars. It's really nice about Luca and Chris Cassidy, all of that. It's about the AMS-2 mission. And it's a very nice documentary. I've been very impressed with it. And I find myself fixated on it. And so I encourage you to watch that. Okay? And so to find the space station, they're having a real party right now. They just had a film crew from Russia that was filming. I don't know what they were trying to do up there, but they went up there, did some filming, and they're back down now. So they had a party up there for about 10 or 11 for a while. But the space station is wonderful and fun to look at. The show stealer for star parties, and it will be visible through on November 10th. There'll be a short gap, and then it'll be visible again. Okay? And on Halloween, the next launch is SpaceX 3 Crew and Endurance. I think it's the name of the crew that you came out with the name. And so that will be the next crew going up to the International Space Station. And did you know that Halloween is an astronomical event? Okay? And what's happening is that these crossover days are called, it's a midway point between the equinox and the solstice. And so there are 4 crossover days. We have Halloween, which is a fixed date on October 31st. Halfway is actually November 7th, but Halloween is a fixed date. And then it's also Lammas Day, May Day, and Groundhog Day. All the other crossover days are the midway point. So I guess somebody was thinking, well, we're halfway there. Let's make an event of it. And so they kept coming up with these crazy ideas for celebration. And so Halloween fits into that. Lammas Day, I guess it's British bread making. And then we have May Day and Groundhog Day. So that's one of the facts you can talk about for Halloween. So with that, stay healthy, everybody, and we'll see you in November.
Thanks, Jim. Tonight's speaker is Professor Stacy McGaugh. Professor McGaugh is the chair of the Department of Astronomy and the director of the Warner Swayze Observatory at Case Western Reserve University. Dr. McGaugh is a prominent expert in low surface brightness galaxies, dark matter, and theories of modified gravity. He's one of the creators of the widely used Spark database, which provides detailed mass distributions for almost 200 galaxies. Professor Jim Schaumbert from the University of Oregon, who's spoken to us before, is one of Professor Magah's collaborators on this database. Dr. Magah received his bachelor's degree in physics from MIT and his PhD in astronomy from the University of Michigan. He was a research associate at the University of Cambridge, a Carnegie Fellow at the Carnegie Institution of Washington, a research fellow at Rutgers University, and a professor at the University of Maryland before obtaining his current position. True confession, I've actually been stalking him online for quite a long time. Please give a very warm virtual welcome to Professor Stacy Magah.
Hello, everybody. Thanks for having me. I trust you can all hear me. Yes? No? Okay, good.
Sounds good.
Indeed.
Yep.
I'm using the setup I taught with through much of COVID, but it often fights back, and it's we've been back in the classroom this semester, and so actually it's like, oh, not the setup again. There's always a microphone that goes wrong or something. So let's see what breaks this time. Let's see if we can share that. And off we go. Okay. So yeah, I'll be talking about the acceleration discrepancy, which is better known as the dark matter problem. But that's a little bit of a misnomer. And as you mentioned, Jim Schaumbert, who's here on the Zoom, is a primary collaborator on this, as is Dr. Federico Lelli, who's at the RCA Observatory in Florence, Italy. Since the eruption on La Palma was mentioned, I quickly added a slide here. I observed there back in the 90s. It's a lovely site, good seeing, and it's off the coast of Africa. So La Palma is this northwesternmost of the Canary Islands. It's a Spanish possession, and the observatory is at the very peak of the old volcano. And it's you see all those wiggles. It's a really a ride you want to take Dramamine for before you go up. And this whole bit here is sloughed off. It looks like somebody just took a giant ice cream scoop and scooped out that side of the mountain. So it's been very dramatically active in the past, and so it's not too surprising to see it acting up again, I guess. So, you're always surprised to see that in your own lifetime. So I like to start this talk off with a philosophical quip. What gets us into trouble is not what we don't know. It's what we know for sure that just ain't so. And I've heard this attributed variously to Yogi Berra, who at some point said everything, and Mark Twain, but after some hunting, I think the correct attribution is Josh Billings, though even there, it doesn't seem to be a direct quote, but more of a paraphrase. Josh Billings was a contemporary of Twain's, but there were a lot of people then too. And so, we get these ideas in our heads and we kind of stick on them. And so that's what he's warning against, is that just because we're sure of something doesn't mean it's actually true. So a few things that we know for sure. As Newton taught us, force is mass times acceleration. Then there's the Poisson equation, not the Newton equation. It's an expression of Newtonian gravity, but it's took a while for Poisson to work out that the relation between the gravitational potential and the density of mass is this funny looking equation. And then that comes down to the acceleration being related to the gravitational potential. And all that really means is that the velocity, how fast things are going, is related to the mass divided by the radius. And that's really all you need to know for this entire talk. Therefore, the universe is filled with non-baryonic cold dark matter. Okay, well, wait, that's a bit much. I see things popping up in the chat. I cannot see anything besides the chat indicator. So if you want to ask a question, then interrupt me. I want to talk about the evidence that there's something wrong, sort of the roots of this here tree, and then all the possible fruits, the ideas that have been hypothesized to explain it. One of the classic examples is the rotation curves of spiral galaxies, the speed at which things orbit as a function of distance, comes up to a constant and more or less stays there. But v squared is m over r, that should go down. It doesn't, and that's one of the roots of the problem. If you look at really big clusters of galaxies, these events discrepancy in a number of ways. These yellow blobs here is a galaxy in a cluster. Measure the redshifts for those things as Zwicky first did. And you find they're moving way too fast with respect to each other. To be bound unless there's a lot more mass there than meets the eye. You also see these dramatic arcs. Those are background galaxies that have been gravitationally lensed. And again, you need a lot more mass to do that than what you can see. There's also an intracluster medium of really hot gas in between these galaxies, and that is too hot to hold down. It would evaporate into intergalactic space, again, unless there's a whole lot of gravity to hold it down. So that is one of the main roots of the problem. Another is large-scale structure. This is a map of the entire sky. So you sort of imagine it wrapping around our head and up and down, like looking down at the map of the Earth, but now up at a map of the sky. And every dot here is one spiral galaxy or a galaxy, spiral, elliptical, whatever. And those are color-coded by redshift. So you can almost start to see the three-dimensional structure of the universe. And there's a lot of structure, right? There are these big long walls, these empty voids, strong clusters, and so forth. And that is something that isn't easy to make. Gravity will do it, but it won't do it fast enough unless you do something to goose the process. And that's another indication that something more is going on than meets the eye. So the observer's challenge since then is to sort of prune back all the theorists' ideas. There's possible normal matter, exotic forms of matter, modifications of gravity. What can we trim out of this? So baryonic dark matter, I will use the word baryon a lot. That's just a sort of particle physicist term for the normal matter that carries mass, protons and neutrons, things that are familiar to us. So all the normal matter I'm going to call baryonic. And of course, the first thing you think is, well, maybe there's just stuff that doesn't shine. Brown dwarfs, very faint stars, planets, things that are just hard to see. And, you know, 40 years ago, that was at least conceivable. There's a Nobel Prize waiting for whoever discovers this stuff. So people looked very hard since then. And basically, we don't see it. We see all of these things, but not in anywhere like the numbers it would take to actually amount to what we need for the dark matter. Another curious idea is hot dark matter, neutrinos being the obvious thing. Now, again, 40 years ago, neutrinos were not supposed to have mass, but Hans Bethe and others sort of suggested, well, if they just have a little mass, then that could be the dark matter. And the initial reaction was, well, no way, they can't, that would be wrong. But if they do, surely that's the answer. And we're at this weird phase now where one of the major advances in physics in that time is the recognition that neutrinos do in fact have some rest mass, very tiny number, less than 1 electron volt. And yet that's not enough to make a serious dent in this problem. So that's not it either. And so the primary candidate is and remains some kind of cold dark matter, just some brand new particle. All we know is what it doesn't do. It cannot interact with light. It does have to interact with gravity, and it might interact through the weak nuclear force, but we don't know that. And there are a couple of big motivations for that. One is that we think we know the amount of normal mass density in the universe from Big Bang nucleosynthesis. So this is the mass density. All these colored points are different estimates of the baryon density from various light isotopes. You can measure their primordial abundance and use remarkably what we know about nuclear physics, apply it to the first 3 minutes of the universe and calculate how much of these things ought to be there. And they all give you a consistent answer around 5% of the so-called closure density, how much it takes to reverse the expansion of the universe and get it to recollapse. So normal matter comes nowhere close to that. But if separately you go out and measure the gravitating mass, how much things are moving in response to the gravity of stuff out there, it's consistently much higher by a factor of 6 or so. Again, not enough to be to stop the expansion of the universe overall, but a lot more than is in normal matter. So right away, you have this weird situation where we think we know how much normal stuff there is, but there has to be something else out there that's gravitating, and it's not any kind of particle we already know about. That's a good argument by itself. It's not enough. And the other convincing argument that really closed the deal for this kind of dark matter was the growth of structure. So on the right here is the low redshift map of the universe, where you can see all the large structures I pointed out before. On the left is the microwave background. That's a snapshot of the universe when it was just a few 100,000 years old. And the contrast has been turned way up. The real message there is that this sky is the same temperature all over the place. The early universe was incredibly uniform. And so there's only a slight difference between this cold spot and this hot spot of order 1 part in 100,000. Now, gravity is only an attractive force, so it'll make the rich grow richer and the dense spots will become denser over time. But you can't get here from there in the lifetime of the universe. This is a very slow process. And so while gravity will do that, it won't do it fast enough unless you, again, do something to speed up the process. One of the things you can do is have some invisible form of mass. And so that's really the argument that sold us all, including me, on cold dark matter. And it was a long time before I realized that these seemingly absolute requirements made a really basic assumption that we know everything about gravity already. Everything, every time somebody says, we know there's dark matter, there's a caveat. We know there's dark matter, provided gravity is normal, there's nothing new going on out there. And that's one of the questions. Is that true? So let's look at that for a moment. The hands-on leading candidate for the dark matter is these weakly interacting massive particles. So this branch I had highlighted on the dark matter tree, neutrinos out here we've excluded, most of these baryonic candidates we've excluded. So this is the branch we have not yet pruned yet, but we've been working hard on it. And maybe we have, because we've really convinced ourselves, this is an idea coming out of the 80s along with super strings and supersymmetry and all these ideas. And the WIMPs were such an odds-on favorite from that time that we've just been acting like we know this is the answer for sure, even though we haven't been able to find it in the laboratory. It's not for lack of trying. Like I say, there's a Nobel Prize waiting for the people who do this. And so there are many experiments working very hard to look for this. And this is the figure of merit you'll see. This is the interaction probability, how likely one of these dark matter WIMPs is to scatter off a nuclei in the detector. That assumes that they do interact through the weak nuclear force, like neutrinos. That's built into the WIMP hypothesis, but you can imagine dark matter candidates that don't do that. And the original prediction was for a pretty high cross section and for a mass of about 100 times the mass of a proton. And then these lines are some of the early constraints that experiments put. And so by 2008, that gray region had been excluded. And that really excluded where we expected them to live. So, you know, theorists being theorists, they moved the goalposts. So this blue and green patch is the region that was predicted by 2008, informed by the failure to detect things up here. So this is not really where the theory wants it to be. It's just where it wants it to be, knowing that it's not here. I and some of the people who work on these detection experiments were a little distraught when we saw that. It's like, well, you know, really? And the theorist says, oh, yes, it's here. And I'm like, yeah, well, you know, that how much probability is in this tail to low interaction cross section? Because, you know, once we cut this off, it's going to look a lot more probable, just like this looks a lot more probable now that we've excluded that. And the theorist's like, no, it's going to be here. Don't worry, it's got to be here. Well, no, it's not. A decade on, and the experimentalists have made great advances in failing to detect things. They really should have by now if it were there, and it's not. And so at what point do you give up looking? It's like, this is maybe barking up the wrong side of the tree. So I was convinced by all those arguments it had to be dark matter, and in particular, it had to be a WIMP. And then I ran into some systematics in my own data that surprised me and made me rethink that. And so if you listen to a cosmologist talk about this, they'll usually say that rotation curves are flat, therefore we have to have dark matter, and they're often talking about their favorite dark matter model. But they they just overlook what I'm about to tell you about. Just ignore it. So galaxies are interesting places. This is a nearby spiral in GC 6946. This is what it looks like in the optical. In the near infrared, and my colleague Jim Schomburg has really pioneered using these kind of data to map out the distribution of stellar mass in these galaxies. And the near infrared is a pretty good approximation of that. What you see here is more or less where the mass in stars is. And then in the radio wavelengths, we can map out where the atomic gas is, the interstellar gas between the stars. And this is all on the same scale. So this gas really does go out further than the stars. And you need both of those components to make sense of this. So having those components, you can solve that Poisson equation that I showed you earlier, and work out for the observed density, what the rotation curve should be for the stars and the bulge, that little dot in the center, the spiral disk, the gas. And you can add it all up, and it is that black line. That's what the rotation curve should be if nothing funny is going on. If you just have, if just what you see is what you get. And you see, you get this classically flat rotation curve, which is in excess of what is predicted by Newton for the stuff you see. And so this excess is what we attribute to dark matter. Now, it's not just that, right? When we invented the dark matter paradigm, that was pretty much the input. Oh, rotation curves are flat, we need something extra. But it turns out there's a lot more to this story. There's a lot of organization. So the level at which galaxies' rotation curves flatten out depends on how massive they are. So a really big galaxy rotates fast. A really low mass galaxy rotates slow. And that's a very strong correlation called Tully-Fisher. And in particular, what I call the baryonic Tully-Fisher relation, the sum of star and gas mass, that's what's plotted here, as a function of that flat rotation speed. And you see there's a nice strong correlation there. That's not normal. For galaxies, when you plot one quantity against the other, it's a mess. That is the life experience of an extragalactic observer. It just, you never see this kind of a strong correlation. So that's telling us something right away. And one of the curious things to me that I emphasize in the titles that I gave you is that there is a characteristic acceleration scale that is involved. So this is a Tully-Fisher relation again, baryonic mass, sum of stars and gas, plotted against how fast they're rotating. I've color coded by whether a galaxy has more stars or more gas. Doesn't matter, they all fall on this line. And this line is a line of constant acceleration. That's the equation. And basically galaxies all fall along that. So there's a single acceleration scale that is called out by this relation. It's there in the data. Now, I got my start in this business working with Jim on these things called low surface brightness galaxies. So I use that term a lot, so I need to define it. A nice high surface brightness spiral is in the corner there. See that easily on sky survey images. There's a little smudge down here. That's one of these low surface brightness galaxies. It's just taking the stars and spreading them further apart. Now, if you zoom in on that, it's still a smudge, right? You can see why these things are hard to find. And that's one of the reasons we were interested in them, is just how many of them are there, what are they like? And so if you take a deeper image and crank up the contrast, you can see there are spiral arms and the diameter is about the same. I've chosen this pair because they're approximately the same distance away. So the linear size is comparable. The difference is really the surface density of stars. They're just spread out here. And so I, as a young scientist, thought, well, geez, there's a prediction here. Newton told us that the velocity depends on mass and radius. For the same luminosity, you have pretty much the same stellar mass. But you've spread it out over a larger radius in these galaxies, by definition, lower surface brightness. So I predicted, really Newton predicted, that these things would fall off of this Tully-Fisher relation. So here's Tully-Fisher mass against rotation velocity for the highest bin of surface brightness. And then the prediction is that galaxies of different surface brightness will form sort of parallel sequences of Tully-Fisher. The lower the surface brightness, the slower the rotation speed. Well, there's the next bin in green, and that green line shows you what the predicted shift is. And there's the next lower bin of surface brightness, again with blue, and then the dark blue for the lowest bin we could do when I made this graph. And so the prediction is not subtle. There should be a big shift here. And yet, if you look at the data, the galaxies didn't get the memo. They're not doing what Newton said they should do. It's as if it knows about the math, but sort of forgot about the radius, and everything's smack on there. That didn't make any sense to me then, and it still doesn't make any sense to me now. Now you can pick out individual galaxies that have the same mass and the same rotation velocity, and this is a pair, one very high surface brightness, UGC 2403, one very low surface brightness, UGC 128. And those are indistinguishable in the Tully-Fisher plane. Same V flat within the errors, same total mass. It's much more spread out in the case of the low surface brightness galaxy, but when you integrate it up, it's the same total within the errors. But the rotation curves are different, even though the flat velocity is the same, the shape is different, and it's different in just the way that you would predict from the light distribution. So on the one hand, if you look at Tully-Fisher, it doesn't seem to know about the light distribution, just the total. But then if you look at the shape, it knows perfectly well about the light distribution. That's really weird. And it gets worse. If you now, this is measuring in just physical kiloparsecs here. If you normalize the radius by the scale length, right? This is a bigger light distribution than that. You can quantify what that difference is and divide it out. So now this is the same data, but instead of physical radius, we're plotting and normalized to the optical radius. And then they look the same to within the errors. So the dynamics, whatever is going on, knows about the distribution of the light as well as the total mass. So Tully-Fisher already tells you that it tells you about the total mass. This tells you that it also knows about the shape of that mass. So that does matter, just not the way Newton tells you it should. And so this difference has to do with the rate of rise of rotation curves. This is now the centripetal acceleration. So basically the force a star feels that keeps it in an orbit in the galaxy. And this is a tiny scale, right? This is 10 to the minus 10 meters per second per second. Just sitting here on Earth, we feel an acceleration of 10 meters per second per second. So this is 11 orders of magnitude removed from our experience. But that's what holds galaxies together. And you notice that very high surface brightness galaxies, so these bennings is the same color bins again. So really high surface brightness is red, really low surface brightness is blue. And you can see the accelerations are low when the surface brightness is low, they're high when the surface brightness is high. And so again, there's this characteristic acceleration that crops up. One of the ways it does that is in the rate of rise, that central rise. The high surface brightness galaxies have rotation curves that go up very suddenly. The low surface brightness galaxies have very slowly rising rotation curves. And so the dynamical surface density, that is the mass surface density that you infer from the shape of that rotation curve, depends on the surface brightness of the stars, just the way you'd expect it would. Exactly that would be the straight line. And that's not exactly what you get at high accelerations it is, but at low accelerations, there's this kink. And this kink sets in at a particular acceleration scale, a surface density scale. But that's just Newton's constant, relates it to an acceleration scale. Now, if you look at those rotation curves, these blue lines are a few examples. This is what's predicted by what you see. And the points are what you get. And it just looks like a big hodgepodge, right? But if, again, you look at the accelerations, the centripetal acceleration measured by the rotation curve, and what's predicted by the observed distribution of stars and gas, then those things are strongly related. They fall almost right on top of each other. And in fact, they do. So this is what we call the radial acceleration relation. Takes the entire rotation curve and compares that centripetal acceleration to what Newton predicts. So this is what Newton predicts you should get. There were no funny business, no dark matter, whatever. You just get that dotted line. That's true at high acceleration. But again, there's a bend. It bends away from that. And it does so very systematically. It's not just haphazard. There's some dark matter here and none there. This is a really very uniform relation. And again, a particular acceleration scale is involved. So it turns out these three relations, baryonic Tully-Fisher, that central density relation, and this radial acceleration relation, all involve the same acceleration scale within the uncertainties. So these are not, different things that happen to involve an acceleration scale. It's the same acceleration scale. And so this is why I say it's an acceleration discrepancy, because we only infer the need for dark matter. And we infer that there's something wrong at this really low acceleration scale, about 10 to the minus 10 meters per second. So here are galaxies and clusters of galaxies and all these things that exhibit mass discrepancies, but they don't really do that until you get to very low accelerations. If you look throughout the solar system, Newton works fine, Einstein works fine. If you go to still higher accelerations, this is what we feel here on the surface of the Earth. This is the orbit of the binary pulsar that Hulse-Taylor won the Nobel Prize for. So it's pulling a couple hundred G as it swings by its periastron. If you go all the way up to the first LIGO detection of merging black holes, that's at a ridiculous 10 to the 11 meters per second. So, there's 20 plus orders of magnitude here, and there's just no hint of any funny business up here. Gravity works fine. It's only at really low accelerations that the problem kicks in. And it's an acceleration scale. It's not a size thing. It's not the galaxies are big or the universe is big. It's not length scale. It's the acceleration scale that matters. Now, what really shocked me when I first ran into it was that, my prediction was wrong. That was basically what Newton predicted. And the only theory that got this right in advance was this theory called MOND, which is not to do with dark matter at all. It's the other branch of the tree of saying, geez, maybe it's not dark matter. Maybe we have gravity wrong. We have to change the equation. That is to say, all the evidence for dark matter, of which there is a copious amount, that's ambiguous. We're assuming gravity is right. Well, maybe the equation is wrong. And so that's what Milgram says, can I find an equation that works? And he, way back in 1983, before most of the things that I told you were known, it was known then that rotation curves were flat. It was known that a Tully-Fisher relation existed, and that was pretty much it. And he said, well, the length scale thing does not work, but an acceleration scale might. And so he came up with a force law that was modified at that. Now, I only learned this myself by a chance encounter in Middle Earth. I was a postdoc at Cambridge at the time, so literally Middle Earth, not quite Oxford where Tolkien was, but he came through and gave a talk, not knowing who I was, and I was working on these low surface brightness galaxies and really struggling to understand why the prediction had failed, just pounding my head against that. And he came by and said, oh, well, if there are these low surface brightness things, then they should do X, Y, and Z, one of which was fall on Tully-Fisher. So I scraped my jaw off the floor and went back to my office and read his paper. And I was struck to see this statement that disk galaxies with low surface brightness provide particularly strong tests. Now, he wrote that a decade before, we were working on it. And at the time he wrote it, people mostly didn't believe these things even existed. And that's the struggle we've been having at that point. Look, we see him. Here's an example. And yet he's making prediction for what their dynamics will be a decade in advance of that. And so the funny thing is that, you know, I immediately started rejecting the idea. And when I read that, I remember thinking, well, now I have the data to test this stupid theory. And so we'll finally falsify it. I mean, that was the attitude. I was sure it was wrong. And so, you know, as I just went and checked the data that we now had, obviously it was going to fail, right? Well, so that Tully-Fisher relation, that's one of the predictions, and the slope has to be 4 because that's what the acceleration scale is. It's a line of constant acceleration. No reason for it to be in any other theory. The normalization of that line, where it falls, depends on this new constant of acceleration that Milgram's theory introduces. Fundamentally, it's just a relation between what you see and what you get. There's no dark matter involved. And what really blew me away is that there was no dependence on surface brightness. The fact that these different colored points representing different surface brightness galaxies all fall on the same line was a genuine a priori prediction of the theory, because nothing else anticipated that. And he predicted other things, so it went down. And so one of the things he said, well, if you calculate the mass to light ratio in a conventional way, then you'll find that within a galaxy, the mass to light ratio rises as you go further out. That's what you see. But as you go to lower surface brightness, the mass discrepancy will set in sooner at smaller radii and be larger. And that's exactly what we were seeing. The shape of the rotation curve should depend on surface brightness. So the high surface brightness galaxies where the stars are dense, you should have steeply rising rotation curves that then flatten out quickly. But as you go to lower surface brightness, they should rise more gradually and only slowly turn over towards flat. That's what we saw. In this theory, there is no dark matter, so the dynamical mass surface density ought to correlate with the surface brightness of the stars you can see. And that's true. It's not a fit. That's just what has to happen in the theory. And ultimately, this is a rule. The modified force law is a rule mathematically to map what you see, what Newton predicts, to what you get, data. So basically, you just are amplifying the Newtonian prediction by this modified force law. So you can fit the data by adjusting the mass to light ratio. We observe the distribution of stars, so the shape of these curves is fixed. We observe the distribution of gas, so that's fixed. But we observe the light, we need the mass. And so you can move these curves up and down by the mass to light ratio of the stars. And that's the one fit parameter that you have. You go and look at individual galaxies. You can scale up those components until you get a good fit. And you can do that over and over and over and over. Now, not all of these fits are perfect, but most of them are pretty good, right? That's a little bit, that's a little awful, that's great, right? That's pretty darn good. This one, right? But this is what happens in astronomy. Not everything is perfect all the time, but most of them work really well. And there are lots of them at this point, nearly 200. Well, actually, I think we're over 200 at this point, individual galaxies. And that was sort of the threshold that Vera Rubin had said, okay, I'm up to 100 rotation curves. They're all flat. That's a law of nature. That's how it works. Right? And just keep going and going and going. All right. So this is a summary, the plot that's basically the residuals of all that, the ratio of the observed to the predicted velocity, color coded by the accuracy of the data. And you can see the most accurate data are most tightly correlated around a fit. And then as the data get worse, the scatter gets bigger. That's what you expect. So these are good fits. Now, we did have that one free parameter as a fit parameter, the mass to light ratio of the stars. Well, we know a lot about stars. Jim is an expert on this. You can calculate the mass to light ratio. These are the mass to light ratios in the blue part of the spectrum and in the near infrared part of the spectrum required by MON to fit those rotation curves. This is the color, just the ratio of blue to green flux. And you can see that there's a trend here that redder galaxies have higher mass to light ratios. That's what you expect as encoded by that blue line. That is the prediction of a stellar population model that is just about stars. It's completely independent of this fitting process. And so you reproduce not only the right normalization, the band dependence, the color dependence, and the fact that you expect more scatter in the blue bands than in the red bands. You really could not have better agreement. So the one free parameter we have is constrained by astrophysical information, and it's smack on. And so, you know, this is a highly non-trivial statement. These rotation curves are not simple structures. They're unique to each galaxy. So every individual galaxy is a test of the theory. So a galaxy like NGC 6946, you see that little dot of light in the center, that's a small bulge, but that concentration of light predicts a feature that you see reflected in that. Similarly, for NGC 1560, which I don't have a pretty picture of because this feature is in the gas component. And yet there's no way this should result in that unless there's a direct connection between the two. So you see that. MON just does that. In fact, you can turn it around to say, okay, I think I know the mass to light ratio. Let's predict the rotation curve. So here's a giant spiral UGC 2885, showed you at the beginning. And this is just a blind match, not a fit, just saying, I think I know what Newton predicts. I think I know the mass to light ratio so well. That's thanks to Jim's work on stellar populations. And this is what it predicts. And you see the right prediction just falls out. There's just a tiny deficit there, which is you expect there to be some scatter. So that's fine. If you do the same exercise with the modern dark matter theory, you're way off. It'll take a whole hour to explain this, but this is what the prediction is, and it's just not even in the ballpark. And yet here it just comes out hands-free. We can do this in any system that's low enough surface brightness that it's in the low acceleration regime where MON applies. So all these little circles highlight dwarf galaxies around Andromeda. These were discovered by the PANDAS survey being done 7 or 8 years ago. And I realized there was an opportunity to make a prediction that they were discovering things really fast. And so we can actually use the discovery, what's the luminosity of each of these things, to predict how fast the stars were moving. And this is that prediction. So this is the velocity dispersion, a measure of how fast the stars are moving. Each of these points is a measurement or a prediction. And each box is one of these different dwarfs. You see there's 33 of them when I made these things. A couple are missing. Andromeda 8's not real. Andromeda 4 turns out to be a background object. MON correctly predicted that that would be the case. Andromeda 27 is not in equilibrium. It's stretched out along the line of sight. But basically, there's good agreement. All those green circles, the prediction of MOND is consistent with the observed velocity dispersion. There's some questionable cases, but that's only got 6 stars observed there, 8 stars there. So here the data disagree, right? The 32 stars is sort of the 277 stars, yeah, that's an agreement. And then there's one case that's just persistently wrong, Andromeda 5. And so, you know, which is the forest and which are the trees, right? This is a real problem. On the other hand, you couldn't predict the rest of these with any other theory. And in fact, the ones I've highlighted with gold stars, those were all a priori predictions. That is, we made the prediction before the data. So within each box, the circle is, the prediction is listed. The points are listed in the order that they were made historically. This is the gold standard of science, right? You make a prediction in ignorance of the observation, then you go out and make the observation and see if it was right. MOND is the only theory that has had any success in doing this. One of the weird things about MOND is that it has something called the external field effect. So it's an acceleration-based theory, and all accelerations matter. So the internal accelerations are what matter for an isolated thing, this case here. But if you're a dwarf galaxy orbiting around a big galaxy like the Milky Way, then sometimes you're falling towards the Milky Way with a greater acceleration than the internal parts of the stars. And so that matters, that external field matters. And the equation changes in MOND depending on which is which. And so you can see that effect in these dwarfs. Some of these things are isolated, and I've drawn up matched pairs that these are pairs of dwarf galaxies that are identical, except one is close to its host and the other isn't. So there should be some difference. And you can see that the isolated case predicts a higher velocity dispersion than not. One can do this in over and over again. Crater 2 was a really good case discovered a few years ago because the predictions are very different. One anticipates, not even really a prediction, but one expects the velocity dispersion of such a thing to be up here in the 10-17 kilometer a second regime. And that's not, I say that's not a prediction, that's really just looking at the data and sort of guessing where it'll go. It's not a theory prediction. MOND makes a clean prediction and it's really different. Instead of being like 17, it's 2. That's different. And that again was made a priori. The subsequent measurement was 2.7. That is so far out of what you expect in the dark matter picture that I had to tack on a piece of this graph to show where it falls. Right? This was just unprecedented. Nobody predicted this except for MOND. So, you know, you'll hear people say, oh, MOND gets this wrong. There's a bullet cluster, there's cosmology, yada, yada, yada. That's all true, but that does nothing to explain why MOND gets all these predictions right when dark matter does not. Dark matter only post-dicts. You can build a model after the fact and say, oh, I explained this. And that's just because you have an infinite number of dark matters and particles to move around however you need to do it. If you want to actually predict something, you use MOND. This external field effect seems to be true in the field as well. There's a hint of that. This is a statistical detection. The thing to take away here is that the best fit value, i.e. how much external field there is, depends on the environment, and it's different from 0. It's not, you know, there's a big overlap, there's a big uncertainty, but formally that's significant. So this is a unique feature of this strange theory that it just has no precedent in dark matter. So not only is it the only way to make these predictions at all, you have this unique external field effect that's predicted only by MOND, for which there's pretty reasonable evidence at this point. Now, the bugaboo is theoretical. What about relativity? We know Newton and Einstein gives you general relativity. Newton and Milgram gives you MOND. You really want to put all three of these characters under the same roof, and nobody succeeded in doing that so far. And it's not easy to do. One does not simply modify the law of gravity. And so you have to recover all the things that we already know work in the context of general relativity. That's proven to be really hard. But there have been indications. So when I first got interested in this in the 90s, it surprised me. And so I understood when it surprised others. And a lot of people just like me originally, just like, no, it can't be true. And cosmologists in particular didn't seem to care what the galaxy data say. They just absolutely didn't care. I thought that was kind of unscientific, but okay, what do you care about? And some of them would like, well, nothing, right? Nothing would convince me of this crazy theory. It's like, okay, well, really, what would make you worry? Well, if the microwave background did something weird, I'm like, well, okay, what would weird be? And so I looked into that, and it's this ratio that you can quantify the distribution of these lumps, the temperature variations on the microwave background sky, by what's called the acoustic power spectrum. So how much power there is at these different angular scales, big scales here, small scales there. So this is basically an inverse angle on the sky. And the only thing that was weird, I mean, I built a bunch of models to try to test this, was that without dark matter, we didn't have a relativistic theory of MOND back then. So the onslaughts I made was like, well, let's just do without the dark matter. And the only thing that really differed was the height of the second peak relative to the first. Now, these models have different normalizations. I've forced them all to be here for illustration, because it's the ratio A1 to A2 that matters, and that's what's quantified there. So the prediction of our dark matter model is that this ratio would be less than 2. 1.95 was sort of the most optimistic prediction. Really, the prediction was more like 1.7. Whereas without dark matter, the prediction was more like 2.4. You can see that, right? This is big, this is small, so that ratio is big. That was made before any of the relevant data existed. So true a priori data. Very quickly started to have data, and these were the most accurate data from the Wilkinson microwave anisotropy probe in the early 2000s. Well, it's a pretty clean test, right? This is where I said it would be without dark matter. This is where everybody said it would be, including me, with dark matter. That's it, right? And quantitatively, it's 2.34, right in the sweet spot of that, within the uncertainties. Okay, clean test, right? Well, not so much. So the same model that gets this part right predicts the third peak should be even lower, and that's not what's observed. So flash forward a decade, and the Planck satellite has extended this way out, even beyond what I've shown here. And there's a systematic offset. So the no CDM onslaughts got this part right, but it gets this part wrong. Now you can say, okay, it's wrong and you can have dark matter, but dark matter didn't do any better. You can fit it because you have more free parameters, but you can't predict it. And so that's sort of where we've been stuck for the past decade. until very recently, Skordas and Zlosnik demonstrated a theory, this is just in the past year, where they get the power spectrum right. So now this is the power spectrum in their relativistic theory that includes Mond, includes general relativity, does all the things you want it to do. And it also grows structure. So this is the galaxy power spectrum, and it basically looks the same. As the data. So this is a great advance, and I wish I were younger and I could actually learn what all this crazy stuff means, because it's hard to make a more general theory than general relativity. Another test that came up lately is that in between the high redshift microwave background, which I was just talking about, and galaxies at low redshift, there's a period called the dark ages, where you just have a universe full of neutral gas around redshift of 100. And as the photons reverse from the microwave background to our eyes, they go through this gas, and if they have just the right energy, they get absorbed by the hydrogen. And that actually goes through two phases, one during the dark ages and one at cosmic dawn, which occurs when the first stars turn on. And the first detection of this was by this experiment called EDGES. So this is the absorption signal that's you expect from that effect as a function of redshift. And EDGES found a surprising result, is that it's higher redshift. You sort of would have thought it was lower in lambda CDM. But the really interesting thing is it's twice as strong as you can get. This is the maximum you can get in lambda CDM, normal dark matter picture. And this blue line is just going back to that same model that predicted the CDM right and saying, oh, what do you predict for this? And that gets the EDGES prediction just right. And there's another prediction here. If we're ever able to measure it at redshift of 100 in the dark ages and not just cosmic dawn, then you should see a stronger absorption signal. That makes assumptions. Maybe those assumptions are wrong, but it's at least a clear and another a priori prediction. Now, this is really hard to measure. The radio frequencies are getting really low here. This happens at 14 megahertz, which is crazy. The atmosphere, the ionosphere cuts you off at 30 megahertz. So to do this, you have to go to space. So it's not easy. So, you know, I keep testing this theory, and sometimes it fails, but more often than not, it succeeds. And it succeeds in ways that the dark matter theory fails at until I tell them what the answer is, and then they get it right. So I want to end here with a snippet from my daughter and Tom Shutt's daughter. Tom Shutt was a colleague of mine here at Case Western for a while. He's at Stanford now. He works on dark matter detection, these experiments that have really now excluded the predicted WIMP regime. And I didn't realize he did that until after we met, because our daughters were best buds in school. And so it happened one time, in fact, at that 2008 conference where that prediction for the dark matter was shown. We had a conference, and both of us, for somewhat different reasons, were skeptical of the moving of the goalposts that the theorists did. But it happened that that conference was held at the same time as my daughter's birthday. So when I came home, the house was full of kids, and Maddie was there as her best friend. And I turned to her and said, "Oh, Maddie, I was just working with your dad." And, you know, of course, we would both claim not to bring our work home, but she looked at me and said, "I thought you worked against each other." And Isabel wasn't going to have that, so she immediately spoke up.
dark matter does too exist. If dark matter didn't exist, then the eighth dimension would not fit into the quantum theory. No. We are correct today. No. The eighth dimension is not a human by the quantum theory of eight.
And so that pretty much sums up the past quarter century of my experience in the field. Thanks very much for your attention.
Thanks a lot. That was really nice. So I think if it's okay with you, maybe we can squeeze in just a few questions. We're running a little late.
Sure.
So we might have a few less questions than we would normally take, but let's try to do it the way that we did it last time, which is essentially that if you have a question and you want to ask it yourself, type into the chat that you want to ask a question, and I will call on you, and then you can ask your question. Or if you want me to pose it for you, just type it in. Okay, so Sanda Prakash has a question.
Hey,
Go ahead.
yeah, thank you very much for a very dense lecture. I think I will have to re-go back and probably read it 10 times before I'll get it. But I
There's
have
a
just,
lot.
yeah. So two things. One, if it is okay with you to share your email addresses so that I can continue asking my questions. But I'll ask two questions. Something that I'm thinking very simplistically. Let's assume a system where you have a central body, like a sun and an earth. And let's assume that the sun is rapidly going through the mass energy conversion. That the change by now that the earth is rotating around based on the simple, right now we'll just assume GMM over R square. But the M, which is the sun's mass, by the time it's not a gravitation is not instantaneous at a distance. It is going to be seen at a speed of light much later on. So at the time that this gravitation is going to start from the sun and control the earth, it is assuming based on the mass 9 minutes ago, while in the meantime the sun's mass has already reduced. The reason why I'm bringing this simplistically is because I'm looking at the galaxy and I'm seeing the outermost, I guess, legs, if you want to call, are rotating faster. My thinking suddenly was, hey, that was the gravitation when it, in its original state, whatever the mass of the center was, eventually took 10,000, 20,000 light years. So what it experiences at the edge is not the mass that existed at that time, but it was 20,000 light years ago. So, and that effect is similar on a shorter distance, which is the inner parts of the arms. It will be slower because now it's seeing a reduced mass of the center. I don't know if I'm communicating it correctly, but
Well, so no, I think I grasp what you're saying, and you're right that there's a big time difference there. And so if there's a lot of mass energy being radiated out of the center, then the outer parts won't get the news for a long time. However, the amount of rest mass that's actually radiated away is tiny. You know, the stellar fusion is less than 1% efficient, and it only involves less than 10% of the mass of the star over its 10 billion year lifetime. So while you're right in your thinking, it's just that the amplitude of this effect is so tiny, it's not going to be noticeable.
Is this the same case with the sun as with the center of the galaxy, where you expect a much denser and higher level of reaction, meaning converting into from lower to the higher elements? So
starlight is basically set. I mean, the nuclear physics is the same, right? So hydrogen to helium is 0.7% rest energy conversion. Everything else that you do above that is extra, but it's not a lot extra. That first step is the big one. So it just doesn't add up to that much in terms of the gravitating mass.
Okay. And my second question is, when we see, as we go farther and farther, we see galaxy receding away at a much faster rate.
Mhm.
But the galaxy that I'm seeing at the very edge, let's say, 10 billion light years, and I'm only getting that light now, to then say that the universe is expanding is basing your assumption 10 billion years ago data. It's like sewing my coat today based on my early childhood measurements. So
Right.
in
You're right. I mean,
just one more sentence.
Sure.
On the shorter distances in the local group, we see blue shift. So my thinking is, maybe if everything was happening instantaneously, maybe the universe has already started slowing down, or has reached a state and is now contracting, but the only time I'm going to know is 10-15 billion years from now. So how come our data is based on old data, but we are making predictions as of today saying it's expanding?
Well, that's what we see, right? I mean, just empirically, if we plot the data, the amount of redshift that we observe scales with distance. So
yeah, but
right.
the data is 10-15 billion years old data, and because the light is still reaching us from the very long past. So
well, we don't, you're right that we see galaxies as they were when they emitted that light.
Yeah.
So we don't know what's happened to them since then, but we do know that the motion as we observe it now is away from us, and that's consistent with this overall picture of expansion. And in fact, the modern claim is that it's not just expanding, but the rate of expansion is accelerating rather than decelerating, as you would expect. So there's certainly something funny going on there, but I won't pretend to know what it is.
No, but you keep saying is expanding, while what you're saying was expanding 15 billion years ago, because the light started a long time back.
No, I don't think that's conceptually correct, because if you have a medium that's expanding and tracers within that medium, the fact that you see it now, that's what it was doing at the time. Maybe it's doing something different now, but what we experience now is that expansion. Right, so you're talking about what we will experience if it's done something different in our now 15 billion light years away. We're not going to experience that for another 15 billion years. So I think it's fair to say that it is expanding now, because that's our experience now. Simultaneity is not well defined in this context.
Yeah, I understand. I'll talk to you offline. I want to give somebody else to ask questions. But if you don't mind providing an email, I'm a duck fan. I'm also a duck. Just want to let you know.
Okay.
So Lon is wondering, in light of the lack of evidence for WIMPs, what additional evidence would be needed to make MOND more convincing to more people?
Well, I've been asking that for a long time, and it depends, right? Everybody has to set their own standard for that. And I would argue that that standard has been met many times over already. We've made many predictions. They've been checked out over and over again. And some people have been convinced by that, and other people are just don't want to deal with it. And so it's more a matter of attitude now than what the next thing is. So for example, the bit about the power spectra of the microwave background that I closed with was for a long time people who didn't want to acknowledge MOND had any efficacy whatsoever. And a lot of people really hate it. I'm not quite sure why that is, but a lot of people just hate it. And they're not objective about it. And so they would point at the microwave background and say, look, it can't do this. And as I showed, for a while, that was true. And now there's this theory that says, okay, this is how you would do it. And so that is the standard that they set. And now that it's been met, they're like, well, I don't like that theory. Well, okay. Yeah, there's an old cartoon with Yosemite Sam and Bugs Bunny. And of course, Bugs tricks him and said, I dare you to cross this line. Well, I'm crossing it. And so Bugs backs up and draws another line. Yeah, I dare you to cross this line. Well, I'm crossing it. And he just does this until he walks Yosemite Sam off a cliff. And that's what I feel with, like, dealing with some of these people. Dark matter has become a religion to some of them, and it doesn't matter what. There is nothing will convince them. It's a matter of faith, not science. That's been my experience for a quarter century now. It's ridiculous.
Thanks. Pat said that he's heard that some dwarf galaxies don't seem to contain dark matter. Is that true?
So that is the claim. There are these things called DF2 and DF4, ultra diffuse galaxies. I think it's a little more nuanced than that. So for example, the first example that was claimed to have no dark matter, NGC 1050 DF2, if we had been provided with the luminosity and known that this thing existed, then we could have predicted its velocity dispersion in advance, just like we did for all the dwarfs of Andromeda. And it's close to the limit of not having dark matter because the external field effect seems to be pretty large, and that's the way the math works. It's not right in MOND that it should have zero dark matter, but it's close enough that it's all within the errors. You know, when they first said that, there was a lot of hype about it. No, this is the death of MOND, blah, blah, blah. And so we looked into it, and yeah, sure enough, we could have predicted it. So, you know, that doesn't have much credibility with me. It's again, they want to believe this. Now, it is a good test in principle, and one that we tried to make ourselves 5 or 6 years ago. And with systems called tidal dwarf galaxies, basically little galaxies that were formed in tidal interactions between giants. And that's a mechanism that should be very good at shredding off the dark matter. And so those things, if dark matter is right, they should have no dark matter. And if MOND is right, you can't shed the force law, so they should appear to have dark matter if interpreted that way. And in fact, we found that they don't seem to have much dark matter, which is to say that's a point in favor of the dark matter theory. Now, it turns out, and we haven't been making a fuss, there's so much hype. There's just, you don't hear about Crater 2, right? That was an amazing a priori prediction. Why don't you hear the hype about that? It's as important a case as any of these things without dark matter. To the extent that's true, I think that's, like I say, I think it's a little exaggerated. They're in a limit that's close to that, maybe. But you know, the thing is that in order to get to that state in the dark matter theory, you had to have had some non-equilibrium event. And what, you know, when we ourselves thought, okay, this is the proof of dark matter, it can't be MOND. And then we looked through the time scales, and there was no way that these systems that appeared to have no dark matter were in equilibrium, regardless of the theory. And so that's what you invoke in dark matter. All those predictions that I showed you, You ask people, oh, well, you know, how do you explain that in dark matter? Oh, they're not in equilibrium. Okay, well, that's lame, but that's the lame excuse we have to use in MON too, these things that they're just not in equilibrium. And that's true in either theory, so who cares?
So Jim made a comment in the chat that's probably worth sharing. He said, dark matter as a paradigm cannot be falsified.
Yeah, I've struggled with this a long time. How do we know, right? Once you've convinced yourself, and the evidence is copious, there's no doubt that there's something wrong. And dark matter was the first thing we thought, and it's the more obvious choice, right? You want to say, okay, maybe there's some mass we can't see, or you want to change basic laws of physics. You know, early on, that was an easy call. So, you know, when I first encountered this problem, I had that thought, well, geez, how do I know? How do I falsify dark matter? Should it happen to be wrong? And the answer is you can't. And every time you think it makes a prediction that you can test, then there's a way to weasel out of it. One example is that the distribution of dark matter is predicted to be cuspy. That's wrong. The distribution of mass excludes that prediction. Does that exclude the theory? Well, the theorists said it did 20 years ago. Now they're like, oh, no problem. We can rearrange that, feed black, blah, blah, blah. Same thing for the microwave background. The reason I made that prediction was because that was what the cosmologists cared about. And I wanted them to have the same shock that I had, that, you know, my data were telling me this thing I couldn't believe. And they just rejected the evidence. I mean, the second peak came in exactly where I predicted. And it took me basically all those 20 years to figure out they created, never published, just created this myth, this alternative reality in which that prediction did not come true. I could tell you for a long time about how that, it took me a long time to figure it out, because you know, I showed it to you how it was true. But the first data that tested it were from the boomerang experiment. And so I wrote a paper and said, okay, it works. The next experiment was called Maxima 1. And it, you know, I looked at it and it showed exactly what I expected. And so I was like, I can't write a paper every time these people publish more data. You know, I won't have time to breathe. And so I didn't. But there was a discrepancy between those two experiments in terms of the amplitude, the absolute amplitude of the power spectrum. That was irrelevant to my prediction. I predicted the ratio, the amplitude divides out of that. But because I had written a paper, what seems to have happened is that people associated my prediction, they conflated that with the first data. And in the first data were wrong in this one way, so the prediction must also be wrong. And that's incorrect, but that's the conclusion they leaped to because it's what they wanted to believe. It's really just confirmation bias.
So I'm hoping we can squeeze in just two more. Craig is wondering if there's been a theory developed to kind of explain the underlying physics associated with MOND. So kind of on a more fundamental level.
Why does this happen? That's a great question. Next. I don't know, right? You know, there is this new scale that is really unexpected. I mean, going back to how do we know it's not dark matter? Well, cold dark matter is scale free. That's a basic tenet of the theory. And here's this scale. It's a case of who ordered this. And so there are various attempts to come up with an underlying theory. I don't find even the new one I talked about from Skordas and Zlochnik, I don't really find them satisfactory for exactly this reason. It seems like there should be some fundamental principle that causes this to be the case. And I don't know what that is. People make the analogy that, gee, this scale, this acceleration scale is comparable to the acceleration at the Hubble radius, basically the expansion of the universe, Hubble time, Hubble speed, Hubble radius. You can make an acceleration out of that. And it's numerically coincident. So maybe it has to do with cosmology in that way. Maybe it seems like a coincidence. So I don't know. I just don't know why this happens.
So the last question comes from Jim, who teaches a class in astronomy. He's wondering if there's a particular website or textbook that you would recommend that describes some of this. And Jim mentioned David Merritt's book.
So
in a
David
comment.
Merritt has written a recent book that's sort of a philosophical take on this whole thing that addresses many of these issues, especially the philosopher of science approach to how do you tell the difference between theories like this. So that is a good resource. The technical stuff, there are a lot of review articles, but written at a high level. So there is a Scholarpedia article by Milgram that lays out the theory. I have my own Mond pages. So if you Google my name and Mond pages, that'll come up, where I've tried to list some of these issues and also talk about them some on my blog, Brighton Station. But right now there is no textbook. The closest thing is Milgram's Scholarpedia article there, but there are really a lot of high-end technical things because the sausage is still being made, right? So it's not textbook stuff yet. The acceleration scale, that's well established, that's empirical, that ought to be in the textbooks, and it's not. And this is one of the points that David Merritt makes in his book. This has been known for a long time now, and people are just not going to talk about that because it's really inconvenient.
Well, thank you very, very much again. It was really great to hear about all these things and to hear you talk about all of this.
Well, there's a lot. It's fun to talk about. It's a puzzler, that's for sure.
Yeah, and we really appreciate you staying up so late to hang out with us.
Yeah, I turn into a pumpkin usually by now. So.
Well, thanks again. I have to say one other thing, though. I'm very disappointed in Jim. He promised lots of heckling. I don't know what happened there.
Yeah, he's pointing out that his hair is still darker than mine. He hasn't been department chair. So. Well, thank you very much for your attention. It is fun stuff to talk about. And I think the great thing is that clearly there's still things to learn about the universe. Sometimes you'll hear people saying, oh, science is over, we know everything important. No, we don't. There are fundamental things still left to be discovered.
Well, thank you very much again. And thank you everybody for coming. It was nice to see all of you. I hope to see you again next month. And Stacy, I'll follow up with you later.
Okay, thanks very much. Good night.
Take care.
Martha, are you there?
Are you trying to talk to me?
No, Martha. I was wanting to know if the downtowners are going to meet at noon on the 5th.
Oh, Margaret, well, stay tuned to your email.
Oh, okay. I'll check with her later. Okay,
Yes,
thanks.
yes,
Enjoyed
Linda.
the program.
Okay.
And yeah, okay. I enjoyed the program. Glad I could tune in. Bye-bye.
Great, thanks
Thank you.
for joining
Bye-bye.
us.
Bye-bye.